All right, so before we went on Thanksgiving break, we talked about Pythagorean theorem, right? So a squared plus b squared equals c squared. And on Monday, we just really drove that home, and on Tuesday, we did a lot of different applications. Today, what we're going to do is we're going to put you guys into a different situation. In today's lesson, where we're looking at special right triangles, what are we asking from you is basically these three objectives for today. One, I want to make sure you guys have the models memorized. There's not really a lot that I ask you guys to memorize in this class. So you might argue otherwise, but there's really not. I teach you guys how to use the information you have and how to at least get to where you need to be. This is one of those things where you really should have it memorized. If you are going to any type of construction trades or building trades of any type, these are two models that you will use daily, and that is a guarantee. And the sad thing is most people don't, I shouldn't really say it's the sad thing, but the people in those trades don't even realize what they're using when they actually get to doing it. They just know it and they go with it. So it's really kind of important that you guys understand the basis behind that and how we use this in building. When we look at a lot of the formations that are in homes and the way that the walls are studied, you know, basically your top two are 30, 60, 90 triangles and 45, 45, 90. And so we're going to be looking at those today. What's nice about these is with Pythagorean theorem, you need at least two sides in order to find the third. With these are special triangles. These are very unique. These are relationships that exist only with these two types of triangles. That's why I call them special rights. They're right triangles, and they have unique outcomes. And again, the nice thing about them is all you need is one side, and you can figure out the rest of the triangle. So let's first go into the 45, 45, 90. Tell me some things you guys already know about 45, 45. Okay, so we have two angles that are the same. It's a 90-degree angle. If the two angles are the same, what type of triangle is that? No, this is the right triangle. Talking about the sides. If two angles are the same, what type of triangle is it? No, not equal. I don't remember that. That's isosceles. Good. What does it mean to be isosceles? Okay. Two of the same sides. Very good. Okay. I know you did. I suppose I'm listening to you. All right. So let's say for a minute that this is x and that's x. So we'll throw my two unknown sides, right? Well, again, if it's isosceles, the two sides are going to be the same, x and x. What's nice about it is then what we get is x, x, and then whatever the side lengths are, that's x times radical 2. And you'll see that same model on your reference page. If you turn it over and look at the back page of it, page 2, you'll see the 45, 45, 90. When the two sides are the same length, and the hypotenuse is the length of the side times radical 2. So let's try this out. In my first example, my side length is 8. 45, 45, 90. What does that tell me about my other side? It's got to be 8. They're the same. So that, what does that tell me about the length of my hypotenuse?
16 radical 2.
Nope. Just 8 radical 2. So it's just whatever your side length is times root 2. Hey, look at example 2. What do we have?
Wait, that's the answer?
That's it. You're done. Hope you guys like that. Really don't do a lot of math here. Eventually we'll get to somewhere and do some math, but it's not a lot of deep math to do. Take a look at example 2. What do we have? What type of triangle do we have? Is it any special right triangle? How do we know? Brian?
It's got the 3, 1, 2.
So, is that what makes it a special right triangle? What makes it special?
45.
So any triangle has a 45? So the fact that I got a 90 and I got a 45, what does it tell you about this angle then? That's how we know it's going to be a special right. So 45, 45, 90. Now, Brian already said, well, we got the 3 root 2. Well, what does the 3 root 2 represent? Length of the hypotenuse. Remember from our model, the length of the hypotenuse is the length of the side times root 2. Ta-da! 3 and 3.
I really.
We can look at it right now. It can get more difficult. But this is the, I mean, you guys kind of get what we're looking at here? Straightforward. Okay, Sam? You on board? Are you on board? Taylor? What about you, Mackenzie?
I'm good.
Any good information on the phone? No, I didn't think so. Okay, it's a little bit different here. And what type of shape do I have there in example 3?
Square.
It's a square. And squares, when you draw the diagonals, always create a 45, 45, 90. Just be aware of that. And that's because remember the diagonals of a rhombus bisect the opposite angles. And so the squares of a rhombus, the diagonals bisect the opposite angles, and in a square, the opposite angles are 90 degrees. Bisect the 90, you get 45 degree angles. But it's a long way to get it. It's all pulling together here. So if this is 3 radical 2, does that represent the hypotenuse, the side, the angle? What is 3 radical 2? That's the side. So this is 3 radical 2. What's the side down here? Try that at home. How do you find the hypotenuse?
3 radical.
Yes. Okay, so we know that x, we'll put up here, is the side length, 3 root 2 times what? Comes to another radical 2. It's always, no matter what that side even looks like, the hypotenuse is always going to be the length of the side times another radical 2. Every time. So, as we said before, root 2 times root 2 is 3 radical 4. But what's the square root of 4? So we got 3 times 2, which is, therefore the length of my hypotenuse is 6. Okay, number 4. Is that a 45, 45, 90?
Yes.
How do we know? Okay, we know it's a right triangle. Yeah.
And go the length to the
Therefore, it's isosceles. Therefore, the base angle must be the same. 45. So we do have 45, 45, 90. What do we have in this 45, 45, 90? We have the hypotenuse. And there's no radical next to it. So it's not like we remember we did this on example 2. We can easily see that it was 3 times radical 2. So 18 is definitely being multiplied by something with radical 2. We just don't know what that something is. So we're going to do a little, I mean, just a tiny bit of algebra. So remember that the hypotenuse is, so 18, which is my hypotenuse, is the side length x times what? Okay. Ignore the ugliness of it. I'm talking about algebra 1. And what I'm really talking about is basically pre-algebra. How do I solve for x? And what do I do? No.
Wait, no, don't you multiply that and make it? Oh, no, you don't make it.
Wait, guys, algebra 1. How do we get the x isolated?
Wait.
No. I
Minus
cannot believe
x,
you guys.
subtract
No, there's nothing to subtract. Alyssa,
Doesn't the square root to whatever cancel out?
no. Well, we need to find a way to cancel it out. No, it's not nine. Okay, let's do this. I'll put on my magic pen here so that it erase. Okay, you guys ready? Suppose I had 5 times x is 29. How do I solve for x? Okay, we divide by 5, right? Simple.
Divide by radical 2.
What? No, we can't do that.
Do you not also You said 2, but radical.
So we do need to divide by the radical 2.
That's why we're
If you try to do it in Strong's, because that's a 5.
Oh, I didn't hear that, sorry. So again, the radical 2 and the radical 2 over here will cancel. And then we're left with this ridiculous problem here. We've got 18 over radical 2. But this is something we've seen before. We should know how to handle this.
Multiply by radical 2 over radical 2.
And but again, the shortcut for that is just to take the radical 2, move to the top, right? And then whatever's inside, stay 4. And therefore, x is 9 root 2. Okay, so questions on those? Pretty straightforward. Alright, we've already talked about the rationalizing. Done that. Okay, we're going to pause here. So, the next thing we need to go over are 30, 60, 90s. And at 30, 60, 90, everything's going to be baked on the short side.